which is a positive integer, which is a composite, of course. Okay, we can't write that as a product of primes. We can't factor that. Okay, so let's move on to the next slide, right? So this is a particular figure where you can notice how this locking and unlocking will take place in this so-called public key crypto system. Okay, so the two parties, as we mentioned just before, okay, Alice and Bob. Okay, what Alice she does? She will be encrypting the message using what you can notice here, so-called Bob's public key. Okay, the message, okay, which Alice want to send to Bob is encrypted by her using Bob's public key. Okay, so this is transmitted through a communication channel. Okay, and on receiving the message, okay, so what Bob does, he will be decrypting the message using what, as you can see, using the Bob's private key. Okay, so as we just mentioned before, Alice will be having her own pair of keys, so called public key and private key. As well, Bob is with his own pair of keys, public as well private. Okay, Alice is encrypting a message, okay, using the knowledge of Bob's public key. Okay, on receiving that message, Bob is decrypting that message, okay, using his private key. Okay, so that's why we highlighted this point. The public key locks, whereas the private key, so-called okay, passwords, one-time passwords, okay, whatever we are trying these days, okay, for many e-commerce sites and other things. Okay, so we call them as private keys. They are to be kept confidential, as you all know. Okay, as we all know. Okay, so the private key is what it unlocks, right? So let us move on to the next slide. So I consider one more slide in order to highlight this particular overall idea. Okay, the general idea of a public key crypto system. Okay, so let us observe Bob and Alice are in communication here, and see, this is how the transformation takes place. Okay, Alice is with a plain text. Okay, so what she does, she will be encrypting this plain text. Okay, using what? Using the public key of Bob, as you can notice in the figure. Okay, Alice is doing what? She is with a plain text with her, and she wants to send that message. She wants to communicate that message to Bob. And what is she doing now? She is encrypting, okay, that message, okay, using what? You can notice here clearly, the public key of Bob. Okay, so after encryption, the plain text is now, you can see it is transformed into a ciphertext. Okay, so that's what we mentioned in the very beginning, isn't it? Ciphertext means it is the text which is not easily readable. It is not easily readable. Okay, so this ciphertext is now passing through certain channel. Okay, we suppose this as an insecure channel. So this ciphertext is now received by Bob. Okay, so Bob is receiving this ciphertext. Okay, so as Bob is receiving this ciphertext, what he does, in order to know the contents, what are there in that particular ciphertext, Bob will be using now his own private key. Okay, Bob is now using his private key. What he is doing now? He is encrypting he is decrypting the message in order to get back the plain text which he received from Alice. Okay, so this is the key generation procedure. Okay, so key generation procedure for the two parties in the communication network. Okay, so that they can have the pair of keys. Okay, public key as well the private key. And in the latter stage, we see that how these two are linked. Okay, how these two are linked. Okay, so in order to provide okay, security to us. Okay, high level of security, right? So I hope this particular general idea of a public key crypto system is clear, right? So let me move on to the next slide. Okay, so we now go with some mathematical prerequisites. Okay, I hope many of these are familiar to you, but in order to just brush up once, I considered the basic mathematical prerequisites. Okay, those who are having a sound knowledge about number theory, they can easily follow, and the others who are interested to this fascinating area, cryptography, they can have a glimpse of this. Okay, so the first is about divisibility. Okay, so when we say that two integers are one integer is dividing some other integer, say we say that b divides a, provided the a can be written as a multiple of b, isn't it? Okay, so we say that b divides a, provided what, we can express a as a multiple of b. Okay, so as a simple example, I just considered 91, okay, which is divisible by 13. Okay, why? Because we see that 91 can be written as 7 times 13, right? So let us move on to the next one. Okay, so greatest common divisor. Okay, this is also not new to many. Okay, so what we mean by this, it is the largest integer which divides both a and b. Okay, usually we represent this by GCD of a comma b. Okay, so this particular concept of GCD plays a crucial role in the crypto system what we are going to talk about today. Okay, and then this is about division with so-called remainder. Okay, so what we mean by division with remainder, suppose say we consider two positive integers a and b, and if at all we say that a is divided by b, say, okay, then what happens, we'll be ending up with a quotient and a remainder, where the remainder you can see it is in between 0 and b. Okay, so this is what happens. Okay, whenever a is divisible by b, okay, so a can be expressed as bq plus r, where q is the quotient and r is the remainder when we divide b, okay, when we divide a by b. Okay, so one can observe that, okay, the particular quotient and remainder, okay, they are uniquely determined by a and b. They are uniquely determined by a and b. Of course, for this again I considered a simple example, and you can see that okay, for 60, okay, I wrote 65, but I think I worked out for 64. Actually this is 64 here, not 65. Okay, pardon me. So this is 64 here. So how we can write 64? It is 24 twice added with 16, right? So again, I think I wrote here 65, but it is actually, sorry, 64. Okay, when we divide 64 by 24, the quotient is 2 and the remainder is 16. Okay, so let us move on to the very important what to say, Euclidean algorithm. Okay, so this particular slide shows how to find out the GCD of given two integers a and b. Okay, so what initially we consider? What initially we consider? We consider say a equal to bq1 plus r2, where r2 is in between 0 and b, and then what we do? What we do? We divide this b by the remainder obtained in this step. Okay, so we divide b by r2 and we get this, and this in the next step, this r2 is now divided by r3, and so on. This process is continued. Okay, this process is continued, and where do we end up? We end up with say rt minus 1 as equal to rt qt. Okay, so in that sense, you can see in the last step we won't be having any remainder. Okay, any remainder in the sense the remainder is obviously 0, and we move on to the last but one step wherein we have this rt. Okay, so this rt is what the greatest common divisor of a and b. Okay, so let us work on a simple problem on this. Okay, so that the whole process is clear to you. Okay, so this is what we considered. Okay, we considered two numbers, 2024 and 748, and we try to work on the GCD of both the numbers, GCD of both the numbers. Okay, so if at all we try to apply the algorithm what we just shown, okay, so what initially we do? We divide 2024 by 748, okay, 2 times. What the remainder we get? 528. So in the next stage, what we do? We divide this 748 by the remainder what we obtained in the previous step, which is 528 into 1 plus 220 is the remainder. So divide now 528 by 220 and then divide 220 by 88. At this stage, we got the remainder as 44. If at all we consider dividing 88 now by 44, obviously we end up with the remainder as 0, isn't it? Why? Because 88 of course is nothing but twice of 44, 2 times of 44, right? So what we conclude then? We conclude that the last but one non-zero remainder so obtained is the greatest common divisor of the two numbers. Greatest common divisor of the two numbers. Okay. So let us now look at this extended Euclidean algorithm. Okay. So what this particular extended Euclidean algorithm says? It says that, okay, for the two positive integers, say a and b, okay, the greatest common divisor of a and b can always be written as a linear combination of some other integers u and v in the way what we described here. Okay, how we can write GCD of a comma b? It can be written as au plus bv, where u and v are what? Excuse me, where u and v are some integers. Okay, so I will try to explain this with the example what we have here. As we just noticed, we just worked out computing the GCD of 2024 and 748. Okay, so what we do is we'll now go by backtracking from the last but one step till the first step. Okay, in order to have the GCD as a linear combination of 2024 and 748, what we do from this last but one step, we backtrack till the first step. Okay, so this entirely is displayed in this slide. Okay, so if at all we keep on backtracking, so finally what we do, we see that the GCD so obtained of the two numbers, okay, 2024 and 748, which is 44, as a linear combination of what? The same two numbers where we found them as, so what are u and v here in this case? U and v are -7 and 19. U and v are -17 and 19. Okay, so what one can notice then, corresponding to the given two numbers, okay, there exist two more integers, 19 and -7, satisfying this. Okay, so that's what the extended Euclidean algorithm says, isn't it? So I hope this particular definition is also clear as we worked on a problem based on this. Okay, so let us now move on further. Am I going a little fast or okay? Hello? Anyone there?
Okay, sir. Okay, sir.
It's okay. Okay.
Okay, sir.
Thank you.
No problem, sir.
Okay, sir. Thank you for confirming. So let us move on to the next definition. Okay, so called the modulus. Okay, the modulus. Okay, supposing a as some integer and n a positive integer. Okay, we define a mod n. Okay, so by a mod n we mean the remainder so obtained whenever we divide a by n. Okay, so whenever we express a integer a and a positive integer n in this way, so called a mod n. Okay, by this what we mean, we are talking about the remainder, okay, which is obtained on dividing a by n. Okay, so in this case n is said to be modulus. Okay, in this case n is said to be modulus. Okay, So as a simple example, again, I just considered 85 mod 9. If at all you divide 85 by 9, you will end up with the remainder as 4. Okay. So this is not a big thing. Okay. So the point here is whatever the remainder we are going to obtain whenever we divide a by n. Okay. One can see that the remainder is always in between these integers. The remainder is always in between these integers. What are they? The remainder always lies in between 0, 1, and so on, and minus 1. 0, 1, and so on, and minus 1. Okay. And if at all we consider all these integers, say from 0, 1, 2, and so on, and minus 1. Okay. So we call that as the set of all integers modulo n. Okay. So what by the set of integers modulo n we mean? What by the set of integers modulo n we mean? It is the set consisting, okay, elements of the form 0, 1, 2, and so on, and minus 1. Usually we represent that by Zn or say Z by Nz. Okay, Z by Nz. Okay, so let's move on to the next slide. Okay, multiplicative inverse. Okay, so what we mean by the so-called multiplicative inverse? Suppose say we are with a prime. Okay, I hope by a prime we mean a number which is divisible by itself and 1. Okay, so a prime is nothing but a number which will be having only 2 factors for it, isn't it? Itself and 1, right? So we observe that if at all we consider z upon pz, okay, z upon pz, okay, whatever element we consider in this particular set, for that element there exists always, okay, some other element b satisfying the condition. What the condition here is? This we call as congruence relation. AB is congruent to 1 mod p. Okay, so corresponding to an element A in Z upon PZ, okay, there obviously exists some other element, okay, say B, in such a way that the product of these two will give 1 under what? Mod P. Under what? Mod P. Okay, so by this way, we observe that B as the inverse of A, isn't it? So as you know, suppose say for a non-zero element, a1 multiplied with 1 upon a gives 1, right? So the multiplicative inverse of a is then set as 1 upon a, right? In the same manner, if at all we have ab is congruent to 1 mod p, what is the meaning? If at all we divide this product ab by p, the remainder we are going to get is 1. Okay, so in this instance, we say b as the inverse of a. We say what? B as the inverse of A. Okay. So I just want to highlight this particular point. Okay. The extended Euclidean algorithm, which we just noticed before, okay, it is an important tool for finding out this so-called inverse of an element in ZP, integers modulo P. What is P here? It is a prime. Okay, it is a prime, right? So here we are. Now coming to this basic definition, so-called fundamental theorem of arithmetic. Okay, this is also new to many, isn't it? Okay, suppose say consider a to be greater than or equal to 2, which is an integer. Okay, means a is a positive integer. Okay, so we can factor a as what? As a product of finite powers of primes. Okay, I mean finite prime powers. Okay, a can be written as what? It can be written as p1 power e1, p2 power e2, and so on, say pr power er. Okay, so one can observe that a in this case is expressed as what? It is the product of finite prime powers. Okay, so one can observe that other than rearranging the order of the primes, this sort of representation of A is unique. Okay, this sort of representation of A is unique. Okay, as an example, you can see I considered I considered 11011, which one can observe as the product 7 into 11 square into 13, right? So 7, 11, 13, all are primes. Okay. So this particular number 11011, which can be observed as the product of finite prime powers, right? So let us move on to the next. Okay. Suppose say we have two prime factorizations. One is for A and the other one is for B of this fashion. Okay. So what is A in this case? We are considering it as P1 power E1, P2 power E2, and so on, say Pk power Ek. And how we expressed B? We expressed B as P1 power F1, P2 power F2, and so on, say Pk power Fk. Okay. And one can notice that Ei as well as Fi both are greater than or equal to 0. In such instance, one can observe the GCD of A comma B as a formula given here. Okay, the GCD of A comma B can be computed by expressing two numbers, say A and B, as a prime powers, product of finite. What to say? Finite product of prime powers. Okay. So how the GCD is defined? We just have a look at this. P1 power minimum of E1 F1, P2 power minimum of E2 F2, and so on. Say Pk power minimum of Ek Fk. Okay. So as a simple example, I considered A and B in this way. I took A as 4864 and B as 3458, and one can observe that the number A can be factored as 2 power 8 into 19, whereas the number B can be expressed as the product of primes 2, 7, 13, and 19. Okay, and then by the formula what we just mentioned, what will be the GCD then? What will be the GCD of these two numbers A and B? 2 power minimum of here 8, 1, and 19 power minimum of, in this case 19 power is 1. Okay, here also 1, 19 power minimum of 1 comma 1, and 7 power. Okay, here there is no prime factor for A as 7, so 7 power minimum of 0 comma 1, 13 power minimum of 0 comma 1. Proceeding in this way, we end up with showing 38 as the GCD of the two considered numbers A and B. Okay, so let us move on to the next one. Another important definition. Okay, so-called relative primes. Okay, so we say that two integers A and B are relative primes. Okay, the other name for this is co-primes, provided their greatest common divisor is 1. Okay, so two integers A and B, whenever of greatest common divisor as 1, we call them as what? Relative primes. I think as a simple example here I considered, I don't know this particular, the two numbers are visible or not. I can't say this. Okay. Yes, now. See, what the numbers I consider here? 98 and 65. Okay. So one can observe clearly both are relative prime. Why? Because their GCD is 1. Okay. 65, as you know, you can write it as 5 into 13, whereas how we can write 98? So 98 can be observed as 2 into, I think, 49. So 2 into 7 square. So obviously the GCD of both are equal to 1. So they are relative primes. Okay. So another important definition, right? Euler's phi function. Okay. So this particular function plays a crucial role in the construction of the encryption scheme by RSA. Okay, we'll see how we can define that. Consider say a positive integer n, which is by positive, as you know, it is greater than or equal to 1. We denote this Euler phi function by phi of n. Okay, so by phi of n, what we mean is the total of the positive integers, okay, which are lesser than n and are relatively prime to n. Okay, so by phi of n, okay, we mean the total number of positive integers which are less than n and are relatively prime to n. Okay, so this also called Euler totient function. Okay, this is also called Euler totient function. Okay, so these are few properties. These are few properties. Okay, so if at all we consider P a prime, okay, so obviously one can observe that phi of P is P minus 1. Okay, so suppose say a simple example, if at all you consider 5, okay, obviously you can see that less than 5, 1, 2, 3, 4 are all relatively prime to uh, 5. So obviously phi of 5 is 4. Okay, and now coming to this factorization of n, okay, prime factorization of n, okay. So if at all we can express n as a finite product of prime powers in this way, okay, then the Euler phi function, okay, denoted phi of n can be expressed as n of 1 minus 1 upon p1 multiplied with 1 minus 1 upon p2 and so on, say, multiplied with 1 minus 1 upon pk. Okay, where p1, p2 and so on pk are all distinct primes. Okay, what are they? They are distinct primes. Okay, so I just considered an example, I think, based on this. Okay, I took 78. I took 78, which can be written as the three product of primes, 2 into 3 into 13. Okay, so applying the above formula, phi of 78. So what will happen now? 78 is now multiplied with 1 minus 1 upon 2, multiplied with 1 minus 1 upon 3, further multiplied with 1 minus 1 upon 13, and finally we end up with 24. 24 as the value for phi of 78. Okay, so what is the meaning? There are a total of 24 positive integers which are lesser than 78, and also they are relatively prime to 78. Okay, they are also relatively prime to 78. Okay, so let us move to the next one. So I hope this particular definition as well the properties what we just finished are clear. Okay, so let us move on to the next slide. So in this slide, I would like to highlight an algorithm, so-called fast powering algorithm. Okay, fast powering algorithm. Okay, so this again is crucial for our talk. Okay, so what our interest is in this algorithm, in order to compute g power a of mod n, g power a of mod n. Okay, so what is the basic idea here? What is the basic idea here? What is the basic idea here? We use the binary expansion of a. Okay, we use the binary expansion of the exponent a. Okay, and what it does? What it does? It does what? It makes us the calculation part little simpler. Okay, so that we can have the succession of squarings and multiplications. Succession of what? Squarings and multiplications. Okay, so as an example here I took 3 raised to the power 218 under mod 1000. Okay, so we are working on mod 1000 means the elements in that set will be from 0, 1, 2 and so on 999. Okay, so what initially we do in order to get this value, we first of all try to write the exponent what it is 218 as the sum of powers of 2, as the sum of powers of 2. Okay, so for that what we did, we observed raising the powers of 2 and then looked at how we can get 218 by adding the powers of 2 as 2 power 1, 2 cube, 2 power 4, 2 power 6 as well 2 power 7. Okay, so what this will be now? 3 power 218. This will become now, okay, so let us observe. Let us observe. So 3 power 218. What it is now? It can be written as in this manner. Okay, 3 power 2 power 1, 3 power 2 cube, and so on. 3 power 2 power 7. Right. So one can notice that it is relatively easy to compute such sequence of values, right? Okay, such sequence of values. Okay, 3, 3 power 2 power 1, 3 power 2 square. Okay, why? Because squaring and multiplying is what we are going to do, right? And moreover, as we are talking about the exponent under mod 1000, okay, we won't be getting the digits which are more than 3. Okay, we won't be getting the digits which are more than 3, right? So here is what the table shows. Okay, the table shows the successive powers of 3 modulo 1000, right? So what we consider I as we just observed, I we took as from 0 to 7, and then rising 3 to the power of 2 power I, 2 power I. Okay, so what do we get then? We get these values. Okay, so in what way this is going to help us? In what way this is going to help us? Okay, so 3 power 218 can be observed as what now? As here we noticed, 3 power 2 power 1. So what is the value? 9, right? So 3 power 2 power 3, what is the value? 561. And then 3 power 2 power 4, the value is 721, sorry. And then 3 power 2 power 6, 281. And then 3 power 2 power 7. So the value is 961. So if at all we consider product of all these 5 numbers under mod 1000, okay, we finally end up with showing 3 raised to the power 218 under mod 1000 as 489. Okay, so what is the meaning? If at all we divide 3 raised to the power 218 by 1000, we get the remainder as 481. We get the remainder as 481. Okay, so let us move on to another important theorem. Okay, I hope this particular algorithm is clear to all. Okay, so called fast powering algorithm. So the other name for this algorithm is square and multiply algorithm. Okay, which is very very much useful for finding out some exponent under mod n. Okay, so this is how the Fermat's theorem is defined. Okay, considering say p a prime number and a be an integer, whenever we raise a to the power p minus 1, what does it give? It gives 1. Okay, under mod p we are talking about, make it clear. So it is the case when p does not divide a. Okay, and we get a power p minus 1 as 0 provided p divides a. Okay, provided what? P divides a. So this implies what? If at all if at all I multiply on both sides by a, so what I'm going to get? A raised to the power p minus 2 under mod p equal to a inverse, right? So what one can notice, uh, we can get the inverse of an integer a if at all we go by the Fermat's little theorem, as well the fast powering algorithm what we discussed just before. Or as a simple example, you can observe this. Okay, so 7814 inverse. Okay, one can notice that as 1284. Okay, under what? Mod 17449. So under this mod, this prime. Okay, so the inverse of 7814 is 1284, right? So let us move on to the next one. So motivation. Okay, one can observe that the particular two functions are of great importance. Okay, are of great importance. Okay, in the study of cryptography. Okay, so what the first function is? It is so-called one-way function. Okay, by a one-way function we mean is difficult to compute. Okay, so f is easy to compute, whereas its inverse is difficult. Okay, and the other is trapdoor one-way function. Okay, so by trapdoor one-way function we mean a function f which is mapping from x to y. Okay, with some certain sort of additional trapdoor information we call it as. Okay, it is feasible, means it is possible, right? it is feasible to find for any given y which is in the image of f, which is the image of f, and x such that image of x under f is y. Okay, so we can observe that the trapdoor one-way function is again a one-way function with an additional property. What it is? Some sort of extra information, like we call it usually it as a trapdoor information. Okay, so it helps us. Okay, it makes us possible to find. Okay, for any given y in the image of f, which is in the image of f. Okay, and x in the domain. Okay, satisfying this. Okay, so this particular figure illustrates the basic concept of a function, which is known to all, I hope. Okay, so let us move on to the next one. Okay, so this particular slide is about the syntax. Okay, so how we can have the scheme for a public key encryption. Okay, for a public key encryption. Okay, so usually one can notice that such a public key encryption scheme consists of three probabilistic polynomial time algorithms, which we call them as key generation and encryption and then decryption. Okay, so here is the first algorithm, as you can see. Okay, so what this algorithm does, it takes an input as a security parameter, say 1 power n, and outputs what? Okay, as we are talking about the key to be generated. Okay, so with the input as a security parameter 1 power n, it outputs what? A key k. So we write this as what? Generating 1 power n produces what? A key k. So I hope 1 power n is nothing but strings of all ones, which are an in number. Okay, okay, n bit string of all ones. Okay, so we assume that without loss of generality, okay, any key k, okay, uh, which is output, which is a output by the generation algorithm, do satisfy this. Do satisfy this. Okay. So let us move on to the second algorithm, which is given by encryption algorithm. Okay. So this algorithm, which takes as input, say, a key k, and what next? A plain text message m. Okay. So what is m here? M is a string. M is a string of the binary digits. Okay, zeros and ones. Okay, and what this encryption algorithm does? It outputs a ciphertext C. Okay, so in the encryption algorithm, what do we observe? We observe that it takes as input a key k and a plain text message, which is a binary string, arbitrary binary string, and finally what it output? It output the ciphertext. Okay, so how the encryption is carried out? So encryption is carried out by using the key. Okay, by using what? The key. Which key? Private key. Okay, private key of the sender. Okay, on the message m. Okay, resulting what? The ciphertext. Okay, so let us move on. The third algorithm, what it is? Decryption. Okay, so what by decryption we observe? By decryption, we observe that it takes what? A key k and a ciphertext c. Okay, and outputs what? A message m. Okay. Please mute. Please mute. So, what does this decryption algorithm do? Okay. Hello, please mute. So in this decryption algorithm, as it takes the input as the key k and the ciphertext c, what it does, it outputs the message m. Okay. So as we know, plain text is encrypted. Okay, and ciphertext is decrypted. Okay. So these are few points which one can notice about any general what to say public key encryption. Okay, so these are the general points which one can notice. Okay, for any key, any public key encryption scheme. Okay, So it is required that every key k output by the key generation algorithm, and every message, okay, which is a binary string, as we observed, holds what? This condition. Holds what? This condition. Okay. You can see this condition is quite important here. Okay. Why? Because we are applying encryption function, okay, for k of m, and that result so obtained. For that we are applying the key again using decryption function, okay, to get what? The message m, to get back the message m. Okay. So you can observe that if at all the three algorithms, okay, key generation, encryption, and decryption, are such that, okay, for k output by the first algorithm, okay, encryption k is only defined for messages, okay, of this sort. Then we say that the three algorithms is a fixed length private key encryption scheme. What will be the length of that? It will be with the length parameter as L of n. It will be with the length parameter as L of n. Okay. So here comes the topic of today. Okay. The RSA public key encryption scheme. Okay. So I strongly feel that this particular what to say, public key encryption scheme is a great motivation to many to dive towards this particular area of cryptography. Okay. So we'll see why it is so fascinating, why it is so much important. Okay. So this particular algorithm, okay, was invented by the three great men, okay, by name Rivest, Shamir, and Adelman. Okay. So they were at MIT that time. Okay. Massachusetts Institute of Technology. Okay. So they invented this particular algorithm, which is widely used even today, which is widely accepted, okay, even today. Okay. So let us look at the very first algorithm, as we just seen in the syntax. Okay. So what the very first algorithm is? It is about key generation. Okay. So in key generation, what we do, each entity creates a RSA public key and the corresponding private key in this way. Okay. Whatever entity A we consider, what that entity do? Entity means the party who wish to be a part of the communication network. Okay. So the entity A, what it does, it generate two large random distinct primes P and Q, which are roughly of the same size. Okay. So what it does first, generate two large random primes P and Q. Okay. What next the entity does? It computes the product of the two primes, n equal to PQ. Okay. So obviously P and Q being distinct primes, okay, one can notice that phi of n will be what? It is P minus 1 into Q minus 1. Okay. So, and then the entity, what it does, it selects a random integer e, and this integer e must be in between 1 and phi. Okay. In such a way that the GCD of e and phi equals to 1. So what is the meaning? E and phi are relative primes. Okay. So what the meaning is? E and phi are relative primes. Okay. So what we do then? Okay, we means the entity here does, okay, it uses the extended Euclidean algorithm for computing what? A unique integer d, okay, which also in between 1 and phi, which is also in between 1 and phi, okay, in such a way that e when multiplied with d gives the remainder as 1, okay, when divided by phi of n, we mean. Okay. So what is the meaning here? What is the meaning here? E1 multiplied with d gives 1 means E and D are multiplied inverse of each other, right? So what will be the public key of A then? The public key of A, as one can notice, it is n. It is n. Okay. And the private key, sorry, The public key N is along with the E here. E what we call as encryption exponent. Okay. And what is the private key of A? The private key of A, as one can notice, it is D. The private key of A is D. Okay. So what are the pair of keys?